Okay, hello everyone. Thanks for joining us. I am excited to introduce Martin Suchara, our speaker today. Martin is a computational scientist at Argonne National Laboratory and at the University of Chicago. He's the leader of the Simulations and Systems Trust of the QNX National Quantum Information Science Center, based at Argonne National Laboratory. Prior to joining Argonne, Martin worked as a principal scientist at AT&T Labs and received his postdoctoral training from UC Berkeley and from the IBM Watson Research Center. Of this after getting his PhD from the Computer Science Department at Princeton University. And with that, I would like to thank Martin for joining us today and let him present some of their recent work on quantum networking. Thank you again, Martin, and go ahead.
Thank you, Stefan, for the introduction. In this presentation, I have three goals. I would like to provide a brief introduction to photonic quantum networks and their applications. My second goal and the main focus of the talk is to introduce Sequence. Sequence stands for Simulator of Quantum Network Communication, and it is an open source quantum network simulator that our group developed. And finally, my third goal is to motivate the use of simulation tools in quantum network architecture design and also experiment planning. And this work is collaborative effort of many people who contribute to the Sequence package, and some of the key contributors are listed here on the cover slide. So why do we actually care about quantum networks? What do we hope to achieve once these systems are operational? Well, quantum networks promise many new applications. For example, we will be able to use polarization of light to synchronize clocks with accuracy that's better than was possible before. And also, we could use different encodings, continuous variable encoding, to enable accuracy that surpasses the standard quantum limit. Another quite impressive application in my mind is the ability to perform distributed computing. We all know that high-level bound doesn't allow to use quantum networks to communicate or transmit data and compress data with a bigger than constant gain. However, there is one task that quantum networks can really excel at, and that's distributed computing. It has been shown that certain computational problems can be solved by communicating exponentially fewer bits of information. So in this setting, you would distribute the input to your problem to multiple parties in the network, and you have some computational problem you're trying to solve, and you can do this by saving exponential communication. There are also other applications, sensing. Network security is quite a prolific application. And building a network that is capable of serving the heterogeneous requirements of these applications is a major engineering challenge, but also an opportunity. So what we would like simulation to do is we would like to model these applications and answer questions. How do we build an architecture that can serve the heterogeneous requirements in terms of bandwidth, latency, and security? And there are a lot of trade-offs here in this space. Some of the applications, such as quantum key distribution, they don't really care about bandwidth or latency much, but they care about security. On the other hand, applications such as distributed computing, they most likely care about throughput very much, and clock synchronization latency is very important. So these are quite heterogeneous requirements, and it is important to understand the design space well. Let me show here or explain how quantum key distribution works for those of you who are not familiar. And quantum key distribution is it's basically one of the oldest, if not the oldest, application of quantum networks. There have been companies that have been, such as ID Quantique and Magic, that have been marketing quantum key distribution systems since the early 2000s as a commercial product. The goal of quantum key distribution is to allow secure distribution of keys between two parties. And the reason we need this is because quantum computing actually poses a threat to public key crypto systems. There's Shor's algorithm that can be used to factor prime numbers. And so public key crypto systems that rely on factoring are susceptible to attacks by quantum computers. And therefore, there's the risk that if someone builds a quantum computer, which looks more and more likely that it will happen in the near future, then the encrypted data that is transmitted over today's networks may be threatened. And this is not a problem that can be postponed by too long, because with disk storage becoming cheaper and cheaper, it is very easy for example, for governments to store data that is transmitted over the network in large volumes and perform crypto analysis on the stored data a decade later. So how quantum key distribution helps here is it allows transmitting a key in a way so that the transmission is secure. And after you transmit the key between Alice and Bob, they can rely on symmetric cryptography to use the same key for encryption and decryption. And this picture shows basically a very simple setup with a laser that is used to encode a secret key in here in this case in one of two conjugate bases. So Alice has her secret key and encodes the key bits in the polarization, and Bob then picks his measurement basis at random, and 50% of the time he will pick the same basis that Alice used for the encoding, and he will be able to measure the correct bits of the key. And they used a public channel to discuss which basis was chosen by Bob for which key bit, and therefore they can determine where they would expect a match. And if EF is not present and not trying to intercept the communication, then in a perfect system with no perturbances, Bob would measure all the bits where the bases match perfectly. Now, if EF intercepts the communication, she doesn't know the correct measurement basis. So with 50% probability, every time she tries to measure a bit, the bit may be corrupted by the measurement. And this can be detected by Alice and Bob by performing a statistical analysis on the keys. Now, there is, of course, a lot of technical details that has to be resolved in order to build a quantum key distribution system, and that's one of the challenges. If you try to simulate quantum key distribution, you have to worry about things such as consistency of the key. If you introduce some, for example, dark counts in the detector at Bob, that will introduce errors into the key, and that key cannot be used in a practical system for encryption or decryption, because that would just not work. So one of the challenges we had to address when we were simulating quantum key distribution is we had to implement sort of like the full stack of the protocol to understand how you can do key reconciliation and privacy amplification and so on. So there is a lot of detail that is hidden behind this. Let's switch gears a little bit here. Let's look at another application, and that is teleportation. So teleportation can be used to teleport some arbitrary quantum state psi from Alice to Bob. And what is interesting about teleportation is it requires both quantum and classical communication. First, you use quantum communication to distribute an entangled pair between Alice and Bob. So here we have some entanglement generator that creates an EPR pair, and half of the pair is sent to Alice, and the other half is sent to Bob. And Alice can teleport the state psi to Bob simply by performing an entanglement measurement on the state psi and half of the EPR pair, and sending the classical measurement outcomes to Bob, who then uses these measurement outcomes as a polybasis correction on the other half of the EPR pair. Now, what this shows is that classical communication is something that will be required by quantum networks, and so this deserves a lot of attention. Classical communication will be needed not just by teleportation, but also for synchronization of a lot of the events. Here, if what you can tell from this picture, from this simplified picture, is, for example, that latency of the classical communication is going to be extremely important. If Bob has to maintain half of the EPR pair until he receives the messages, if quantum states decohere over time, we cannot clearly cannot tolerate delays in classical messages indefinitely. So this was a motivation about some of the applications. Let me use this as an opportunity to ask if there are any questions at this time.
I'm tracking the chat window, and I can interrupt whenever there are questions. So everyone should feel free to ask either directly or through the window, through the chat. Right now, I don't think anyone has written anything in the chat window.
Thank you, Stefan. So let me introduce our team. We built the simulator of quantum network communication. And our goal, we had several goals when we started creating this tool. One of the goals is to enable easier experiment planning and validation. If you want to build a quantum network, it's a very expensive endeavor, and no one really knows how to do that. So it is really important to have a tool that enables comparing a lot of what-if scenarios. And our eventual goal is to actually facilitate design of scalable quantum network architectures that can scale with a number of nodes. So far, we have seen mostly proof of concept experiments with perhaps just 3 or 4 nodes in metropolitan areas. But eventually, we will see networks with many nodes covering longer and longer distances. So understanding how the architecture should look like is important. And here you can see that some of the questions we'd like to answer. We would like to know what is the ideal topology and architecture for the scalability and long distance communication. it is not clear, for example, how should entanglement or if networks should be purely viewed as a means to distribute entanglement with certain properties such as latency and fidelity and throughput, and then it is the role of the application to somehow consume the entanglement. And if that is the case, how do you actually distribute entanglement? Do you would the architecture need some reservation system that where the application simply requests, okay, I want entanglement between node 7 and 15 with such and such latency at such and such time, and then the network delivers that? Or would this be more on demand, that the application requests the entanglement on an as-needed basis? And it is also not clear how you actually achieve entanglement distribution. Would you use entanglement swapping on EPR pairs, or would you use something like GHZ states or W states and some clever routing protocol that would allow you to satisfy the needs of the applications more in real time, and perhaps with less reservation and less advanced planning? Another challenge will be synchronization of and control of all the optical components. So if you look at, for example, the diagram of the teleportation experiments in metropolitan test beds, there's already a couple dozen optical components that need to be synchronized, and they need to work towards the same goal. And this is of course going to be a quite challenging problem as the number of these components increases. Simulations can also be used to evaluate performance of specialized network protocols. For example, some of the important tasks are management of entanglement by entanglement generation, distribution, and purification. And there have been many proposals how to improve these protocols. And so simulation is a very convenient tool to plug in the new protocols as they are developed and understand the implications of these performance improvements. And actually the same is true for hardware. We can use simulation to also understand the benefit of building, for example, better detectors with less dark counts, memories with longer coherence times, and so on. Here's the diagram that shows the operation of the individual modules in the simulator we built. In classical networking, people use the OSI model to distinguish functionality, and at the lowest layers of the OSI model, you have hardware, the physical layer that is responsible for controlling hardware. At the highest layer, layer 7, you have application, and in between you have the middle layers that are responsible for things like routing and congestion control, and so on. For quantum networks, we don't yet know how the protocol stack should look like. We don't know if we should use the exact same stack that works so well for the internet, or if we need something slightly different. So for this reason, we decided to introduce a modularized design for the simulator. Here we actually allow communication not just between the adjacent layers of the stack, but also, as you can see, communication, for example, between a resource manager and many other layers at the same time. And we have done this because we didn't want to impose a rigid structure on the quantum network protocols, and we want to have the ability to explore what structure actually works best for quantum networks. I'm going to talk about a few of the modules here. The resource manager on the left traces the state of quantum memories together with a memory manager. The rule manager, which okay, so I don't have the rule manager, but it is within the resource manager. It applies a rule set to manage the hardware resources. For example, to determine where to allocate resources so that you can perform long distance entanglement distribution. And all of these modules, they are events for these modules are scheduled by the sequence simulation kernel. Our open source release of sequence right now is a parallel simulator that uses a high performance workstation or you can use your laptop or a high performance workstation to perform simulations. But we are also working on a parallel version of the simulator where we separate the simulation kernel onto multiple nodes in a high performance computing system to allow simulation of larger networks. And here are some examples of the functionality that is currently supported by the simulation. At the lowest layer, at the hardware layer, or in the hardware module, we provide modules of single atom memories. We have, of course, models of light sources, single photon detectors. We have quantum and classical channels at some level of detail. We have beam splitters, interferometers. We allow Bell state measurement using elementary optical components. And we have SPDC sources of entanglement. At the higher layers, we support entanglement management. We have implemented basic protocols for entanglement generation, entanglement purification, and entanglement swapping. We are using a network management module that allows applications to reserve network resources to distribute entanglement. And what happens is the application will request a target fidelity for the entanglement and a target time when the entanglement distribution should occur. And we are using this, even though we are using this reservation system, we are actually open in the future to consider architectures, and something we would like to do is consider architectures that are not based on reservation at a specific time, but rather that allow the applications to use entanglement as it is created in real time. And I think it will be very interesting to compare these two models. We know, for example, that the IETF community, there is a quantum internet standardization group. And their view, based on at least the latest meeting minutes, is that reservation is something that they envision for the network. But I think it would be very interesting to compare this reservation model to the more best effort or on-demand system that is more closer to what to how the classical internet today works. We also have the resource management module. I talked about it briefly in the last slide. It is responsible for managing local resources, reservations of local resources in a node, updating the hardware state, and there is the memory manager and rule manager that manages the hardware. And then finally, we have also a rudimentary application layer that implements, for example, entanglement transport between network hosts. We implement quantum teleportation and quantum key distribution. The application layer has not been the main focus of our work, but it would be easy to add additional applications. The sequence simulator, we have online tutorials that can help teach you how to use it, as well as help files and descriptions of the code with comments. At the high level, we are using JSON files to represent the parameters of the simulations, for example, the topology, connectivity, attenuation, and all the various parameters of the systems. The optical components are parameterized as well. For example, for weak coherent light sources, we specify frequency and mean photon number. For single photon detectors, we allow the user to specify things like detection efficiency, dark count rates, and so on. For quantum memories, you can specify actually a number of parameters, not just coherence, but actually I will show a bit more detail about the memory in one of the simulations we performed. So how do you actually validate that a quantum network simulator is performing according to your expectations and the outputs of the simulation are realistic? Well, to achieve this, we performed a couple of simulations of existing experiments. So we looked at a couple of research papers, and we tried to replicate the results. We looked at, for example, here at a paper that performed quantum key distribution over a long distance optical fiber. This experiment is it is a bit old, so the parameters are perhaps not as good as if you were building this system today. But the point of the simulation was really the validation of the simulation system. So here we in our setup we programmed Alice to, just as in the real experiment, to have a light source that encodes the secret key in time bands. We have a quantum channel and a classical channel. The key is transmitted over the quantum channel, and then Bob uses a switch to measure at random each photon in one of the two bases. And we use the classical channel for communication between Alice and Bob to perform all the steps of the BB884 quantum key distribution protocol and the Cascade protocol for reconciliation and privacy amplification. And as you can see here, here are the results
Martin?
of.
In between those slides, there were a couple of questions about the sophistication of the hardware models. For instance, one of the questions was for beam splitters, how they modeled, is the model as a complete matrix? Eric was asking how low level were the simulations of the lasers. Could you elaborate on some of those points?
Yes, our end, so we have fairly rudimentary models. I mean, the lasers, we are using, for example, decoy states. So we modeled that, but I'm sure that there's a lot more detail that could be included in these models. One of our goals is actually to allow the community to help us develop some of the details of the models they're interested in, and actually having even having a list of features that people are most interested in would be very useful for us. So fairly rudimentary at this stage.
Well, for all the people that were asking questions on that topic, if you send lists of demands, I'll be happy to forward it to Martin. We'll also put contact details later.
That would be excellent, yes.
Right now, I don't think there are any other questions.
So let me talk a bit about the validation for the quantum key distribution. So here, what you can see is, well, I mean, this is quite intuitive. As you increase the fiber length, you have exponential increase in the bit error ratio. The blue, I believe the blue dots show the measured rate, and there is also a theoretical rate. Oh, I'm sorry. Right, the blue dots show our initial measured error rate, which was a lot better than what the experiment showed. And one of the things we discovered is we actually did not include the phase modulator error in the initial simulation. So then, after inclusion of that, we were actually able to match the expected result based on the measurement from the experiment. So the experiment is the red dots, and then the right, and our simulation would match that only after inclusion of the phase modulator error. And so this shows that, of course, that validation is very important. We looked at the throughput and latency of Cascade. So here on the left side, you can see the raw bit rate and the key formation rate. So this is on a logarithmic scale, and what is important to realize is the key formation rate is going to be a lot lower than the raw bit rate, because you need to use Cascade to ensure that the keys match. You need to basically like filter out all the errors and make sure that you have a key that is exactly the same for Alice and Bob. And you do that by performing certain parity checks on subblocks. And so Cascade will start with, it starts by creating large blocks to perform parity check. The parity check is violated, then you have to decrease the size of the block and keep repeating the parity checks until with very high probability you are certain that there are no errors left. And at the same time, you have to throw out some of the bits away, because whenever you perform a parity check, you discuss the parity check on the open classical channel between Alice and Bob. Some of the information is leaked potentially to the adversary. So your key becomes shorter and shorter. And this also leads to high latency, because as you increase the distance, your error rate will increase, which is quite natural, because your dark count rate in the detector stays constant, but your throughput is getting lower and lower due to attenuation. So the errors proportionally are a larger fraction of the key. So you need many more rounds for Cascade to reconcile the key as you increase the distance. And so you have basically exponential increase in latency and the costs to do the key reconciliation. We also performed some, here you can see on the right side, we tried to change values of some parameters, but this is not all that important. I think we just did that because we noticed that the parameters of the original experiment, it's a paper that's I think almost 2 decades old now. So the parameters of some of the hardware were not really up to current standards. So we wanted to see the impact of these changes. Here's a teleportation experiment that was performed in Calgary. So what happens here is Alice has a light source and emits a photon that's called a target photon that encodes some arbitrary quantum state. And this photon is sent to the node in the middle, to Charlie. Now, at the same time, Bob will create a pair of entangled photons, and he sends one of them, which is called a target photon, to also to Charlie. And then here, these two photons arrive at the same time, and a Bell state measurement is performed. And then after this entanglement Bell state measurement is performed, the state here that was transmitted in this target photon is teleported to the state here at Bob. And then finally, Bob will perform measurement here in one of the two bases that he picks to measure the state, the teleported state. So this is the setup. And in the simulation, we looked at if really the teleportation is successful by comparing the expected results of the measurement against against what was measured by the simulation, and comparing it against, of course, against the experiment as well. And here you can see that not only the simulation results match our expectation, but also the we can explain the errors, the measurement errors that we can measure, and they roughly match what was reported in the paper. So we use time-band encoding for these photons, and so on the left side is the z-basis measurement, and the early and late states can be distinguished as expected here, but the plus and minus states, of course, in the z measurement, they would not be distinguishable. And for the x basis, of course, it's exactly the opposite. You can distinguish plus and minus, but not early and late. Now, you may be asking, why is the error asymmetric here? On the left side, the z-basis measurement, the error is what? It's about 1 to 2%, and here for the x-basis measurement, it was 6 to 7%. Well, it is actually consistent, because consistent is the setup, because for the x-basis measurement, you need to use interferometer and 2 detectors rather than 1 detector. So you have dark counts coming from both of the detectors contributing to this error.
There is a question right now. Adrian, do you mind asking directly? I'm not certain I can convey your question.
I was just wondering, in your model, how many of the parameters do you fit, if any, or do you take the parameter values from the experimental data?
That's a great question. So we tried to, so the experimental paper had a list of parameters, and we basically like read very carefully the paper, and whenever there was a numeric value or a parameter, we tried to include that parameter into the model. Right.
And did you, so if it wasn't in the paper, did you just fit it, or you make an estimate, or?
I don't know if there were, so I mean, we have not contacted the authors, and we have not, I don't recall a parameter that we would fit. I mean, our model for this work is still relatively crude, so I don't recall a parameter we needed to fit. Is there a specific? I mean, maybe we can discuss also a bit later. But is there a specific parameter you think would be important to fit?
Oh no, I was just wondering about one of the previous plots with the exponential behavior. Yeah, this guy. Obviously, this is a very good agreement with model, but obviously you have only a very limited number of parameters that you would need to adjust to make this model fit. So I was wondering, like this phase modulator error that you took into account here, is that a fitting parameter, or is that something that you extracted from first principles or the experimental values?
That was from the experimental values and first principles.
Okay, cool. Thank you.
Okay, great. Thank you for the question. So finally, I'm going to move to the last simulation we performed. We are participating. Argonne National Lab is building a quantum teleportation network in the Chicago area. We are collaborating with a number of institutions, most notably University of Chicago. And we also have a project jointly with Fermilab and Northwestern. There have been already experimental demonstrations on the quantum link between Argonne and Fermilab and quantum loop, which is, I believe, a 26-mile chunk of fiber. It was used for, if you use it as a loop to go twice around, we used it for a 52-kilometer demonstration of entanglement distribution. And the eventual goal is to build a quantum network in the Chicago region and beyond. Here, what we did is we simulated quantum communication on the Chicago Metro network using some of the fiber we already own, and in addition, simulating also traffic on fiber that is not in use yet, but it could be used to build a more robust and more well-connected topology in Chicago. So we used models of atomic memories, and we performed simulations where we had random requests from applications. So the nodes would request how much entanglement they want to distribute, at what time, with what target fidelity. Each node was configured with the atomic quantum memory. And we looked at things like throughput of the network and memory usage over time. And here you can see a list of some of the parameters we considered. Well, a few of these are constants, but some parameters that we considered for the memories, the detectors, and so on. And you can see that the model is still fairly rudimentary, but our goal is in the initial stage to provide a model or a simulator that basically is able to do the simulation across all the layers. We have a little bit of the application, a little bit of the physical layer, a little bit of routing, and so on. And over time, we would like to increase the complexity of the simulations we can do, and also increase the scale of the simulation. So the quantum internet is within reach, and quantum simulations can help us design networks that support multiple applications. Something that will be important, I think, is considering heterogeneity of technologies. One of the successes of the internet is that you can use TCP/IP to connect basically like almost any hardware technology, and so it is relatively easy for the hardware to evolve, and it can still be supported by TCP/IP. So likewise for quantum networks, we should think ahead, and we should be thinking about how can we, for example, include satellite communication within the same protocol stack. And I think we could also learn from the classical internet some of the things that perhaps work less well is security. Many classical internet protocols are based on trust. If you consider the routing system, routing messages are in most of the protocols are not really authenticated, and it is very difficult to add security mechanisms to existing protocols, because there is basically no flag day in the in the classical internet. You cannot take the network down for a day for maintenance. So we should keep that in mind, and as we design protocols for the quantum internet, I think one of the really desirable features would be upgradability. Be able to design protocols that can be upgraded over time. Here's an acknowledgement of some of the experimental work that is being done at Argonne and University of Chicago. The project I mentioned about using fiber for distribution of entanglement is led by Professor David Ashalom, who is the director of the QNext National Quantum Information Science Research Center at Argonne, that was recently funded by the Department of Energy. And there's also a large number of experimental groups that contribute to this research. One example is the lab of Professor Zhang at Chicago, who is building quantum memories. We have active collaboration with also with Fermilab and Northwestern that uses fiber between the labs. And here, some of the questions really that have been on my mind lately is again, how do we manage entanglement in quantum networks in the best possible way? Here, this picture shows entanglement swapping. This is basically the simplest thing you can do to distribute entanglement over long distances using multiple links, where you distribute entanglement between let's say the directly connected neighbors, and then you use entanglement swapping through performing Bell basis measurement. But in my opinion, there could be better protocols that use W states or JZ states, and this is something I'd like to look into in the near future. Also, I'm interested in the design of and functionality that should be placed within each of the network components. It is not clear to me, for example, if we should distinguish between a quantum router and quantum repeater, or if there should be symmetry and basically like every repeater is also a router. The difference here could be, I mean, degree 2 node could be a repeater, higher degree node that has richer connectivity could be a router. But are there any advantages in making this distinction in the control plane and in the hardware, or should all nodes be just routers? And there are many, many questions like this. So with that, I'd like to conclude, and I'd like to also point out that our team is expanding. We have openings available for postdoctoral appointees at Argonne National Lab who would be able to join the network simulation team. We are looking for people with expertise, not just in computer science and simulation, but also people who have physics background and can act as liaisons between the experimental groups and the simulation team, or people who have more classical background in classical networking. With that, I'd like to conclude, and I welcome any questions from the audience.
Thank you, Martin. This was great, and we already have a couple of questions actually. Wenham, Eric, if you want to go ahead and unmute to ask directly, or yeah, Eric, I see you're unmuted. Go ahead.
Yeah, thanks. Great talk. Thanks so much. I was wondering if you could comment a bit more on what your qubits look like at the code level. So like specifically, sort of what's the formalism? Are they like just density matrix for, with two states? How do you handle things like qubits leaving the computational basis if there's loss or something like that? And I guess tagged alongside with that, I was wondering if sequence can handle continuous variable as well as discrete variable.
That's an excellent question. Thank you. We are using the bracket notation and density matrices to represent quantum states. There is, of course, a scalability issue, and right now we are actually working on the quantum state manager that is responsible for maintaining the quantum states. And one of the unresolved issues is actually how can we distribute the representation, the quantum memory manager, the representation of the quantum states. Right now, everything is running on a single workstation, and we are limited to metropolitan scale systems. But in the future, if we are talking about, let's say, a nationwide network, or, well, basically any network that has more than, let's say, a dozen nodes, we need a way to parallelize the representation of the quantum states. And this is actually something that we are actively discussing right now. We have some ideas how we could have regions where each region, geographic region in the network, has a density matrix and or density matrices of the subset of entangled qubits in that region. But we are actually struggling a bit about what to do about, of course, photons that cross the boundary between the regions. Or if you do entanglement distribution, right, you will have entanglement go between the density matrices that are stored in separate regions. So an excellent question. Short answer: density matrices right now is something we do.
Thank you.
And then I think you asked also about. There was a second part to your
continuous variable.
question.
If it can handle continuous variable states as well.
We don't right now. We don't.
Okay, just wondering. Thanks.
To piggyback on this, so I've used the stabilizer formalism, the efficient representation of stabilizer states for some of my work, and for the restricted cases I was studying, for me this worked well. Could you describe what considerations come in here when deciding whether it's feasible to use that formalism that's much cheaper to implement, but I guess has limited set of states it can represent?
Yes, so I think thank you, Stefan. I think we discussed this maybe briefly, the stabilizer formalism, right? I think it would be interesting to try to implement it. So I understand for stabilizer formalism, you can only track the polybasis states. I mean, that's something that has been, we have used it successfully before in simulation of quantum error correcting codes. And so perhaps, I mean, here in the quantum network context, it could be used as well. Perhaps it would be most suitable for what is called the third generation of repeaters that uses error correction to aid transmission of states between network nodes. So I would say, so we have not really, like, our simulation is more like the first generation simulation right now. But I think as we consider error correction, for example, I think I would like to reuse some of my previous code that allows quantum error correction, simulates the behavior of quantum error correction. I think it's something we would like to do, but right now, really, our bandwidth is somewhat limited by the number of people we have and what we can do.
I see. Thank you. And there's a question from Wenhan. Feel free to ask directly, or
my question
go ahead.
That if somebody wants to implement their own entanglement management protocols, can they easily do that, or do they have to talk to you first and then you implement protocols for them?
So It depends on your goal. So we have the tool is available on GitHub, so anyone can go to GitHub and clone the repository. And you can indeed, so the simulator is modularized. So if you all you want to do is some quick simulation, and you don't care about sharing the code with others, you can just fork the repository and create your local copy, and just change the module or add a module. And that is true at basically, like, and we try to modularize the entire stack. So any layer you can add modules. Now, if you want the code to be part of the open source release, then you would of course have to talk to us. And we are sort of like at the beginning of starting working with collaborators. So I don't know yet how who will manage this process or how this will evolve. But we actually do welcome collaboration, and I think it would be actually awesome if there was interest from the community to help us build some of the modules.
Okay, thank you.
Any other questions from the audience? Also, something that was mentioned midway through the talk, feel free to email with your pet systems that would help to be implemented in such simulators. Okay, if there are no other questions, maybe we can transition to the various breakout meetings that we had planned. Thank you again, everyone, for joining us today, and thank you, Martin, for the presentation. With that, let's just wait for everyone to trickle out, and we'll plan the follow-up meetings.